All right, let's talk about this molecular models lab. If you were in class, you would have used the ball and stick models. If you did this at home, you would be using the PhET interactive simulation, just like we did on the previous practice. Either one works, and you can see the same thing in both of these. To begin, I asked you to fill out this table, and this is essentially the same table that I gave you, um, where it shows the pairs around the central atom, the bonding pairs, non-bonding pairs. These are the lone pairs. The shape that is the result of these things here, and the bond angle that results. So tetrahedral molecules have a bond angle of 109.5, likewise with trigonal pyramids and bent that have two bonding pairs and two lone pairs. If you have three bonding pairs and zero lone pairs, you have a trigonal planar and 120. If you have two bonding pairs and one non-bonding pair, you have a bent molecule, which is 120 degrees for its bond angle. And then if you have two bonding pairs with zero non-bonding pairs, obviously it's linear with a 180-degree bond angle. Okay, let's get into the rest of this here. What we have here with CF4 is 32 total valence electrons. You count that up by taking fluorine, which is in group 17, so it has 7. Multiply that by 4 because there are 4 of them, and add 4 because carbon is in group 14, for a total of 32. The Lewis structure is here, the shape is tetrahedral, bond angle is 109.5, and the polarity would be nonpolar because it's perfectly symmetrical and there's no overall dipole here. All right. Here in H2SE, we have 8 valence electrons. And as you can see, this looks very similar to water. So it's going to be bent with 109.5 degree bond angle, and it's polar. Down here we have PCl3, 26 total valence electrons, shown here in the Lewis structure. That makes a trigonal pyramid or trigonal pyramidal, 109.5, and it is polar. Okay, all bent molecules are polar, and likewise all trigonal pyramid molecules are polar. Okay, I hope you see that trend. Silicon dioxide here at the bottom has 16 total valence electrons. It looks very similar to carbon dioxide because carbon and silicon are in the same group. It has 2 double bonds. That makes it linear, 180 degrees, and it's nonpolar. Most linear molecules are nonpolar as long as the two things on either side of the central atom are the same. Okay, we'll see a difference here in just a moment. Let's see. All right, so this OCl2 has 20 total valence electrons. It has a Lewis structure like this, and this looks linear, but because there's the two lone pairs, that makes it bent like water, and it's 109.5 and polar. SO3 has 24 valence electrons. It has 3 resonance structures because the double bond can be in any of those locations. It does not have a lone pair around the central atom. That makes it trigonal planar, 120 degrees, and it's nonpolar. Even though this double bond makes it look polar, it can be in any of those locations, and it's the average of all 3 of those, so it is in fact nonpolar. Down here we have SO3 2 minus. Remember, when you do these, you add up the total valence electrons and add 2, designated here by this 2 minus charge, for a total of 26. You have this Lewis structure. Don't forget the brackets and the 2 minus charge. This has a molecular geometry shape of a trigonal pyramid, 109.5 degree bond angle, and it is polar. because, like I said, trigonal pyramids are polar. And then the last one is CO3 2 minus. We have, again, an additional 2 electrons for a total of 24. We have 2 additional resonance structures in addition to this one. This double bond can be in any of these places. So it's very similar to SO3. It's trigonal planar, 120-degree bond angle, and again, it is nonpolar for the same reasons that we stated up here in sulfur trioxide. Okay, so make sure that you understand these things. It's very important for something that we do later on when we talk about intermolecular forces. So pay attention to that. Let me know if you have any questions. Thanks.